Okay then, till the last class we have studied about electric potential on the axial line of the dipole and on the equatorial line of the dipole, right? Can you recall that relation? Let us recall. Electric potential on the axial line of the dipole is given by 1 by 4 pi epsilon naught into P upon x square minus a square, no? And then the electric potential on the equatorial line of the dipole is equal to 0. Now this time what I want to discuss is I want to find out the electric potential at any point on the dipole. Okay? Let's say that I take a point M, r theta. Point M, r theta means this point is at a distance r from the dipole, and theta means angle made by the point with the direction of the dipole is theta. We know that electric dipole means it's a system of two equal and opposite charges separated by a certain distance apart. Here, if I take any point M r theta means this point M is at a distance r from the center of the dipole, and we know that the direction of the dipole is from negative to positive, right? Direction of the dipole is from negative to positive. Okay? Then this point M makes an angle theta with the direction of the dipole. Alright? So I'm going to take any point, okay, M r theta. Alright? Yes. So electric potential, this is one of the most important relation, okay? Electric potential at any point M r comma theta, okay? Due to the dipole, where r is the distance of the point M from the center of the dipole, theta is the angle made with the direction of the dipole. Okay? So let us draw an electric dipole. Electric dipole means it's a system of two equal and opposite charges, okay, separated by a distance, say 2a apart. If O is the center of the dipole, this distance OA will be distance OA will be A. Distance OB will also be A. Right? Now I'm going to take any point M, such that this M point M is r theta, means M is at a distance r from the center of the dipole, and theta is the angle made by this M with the direction of the dipole. Alright? It's obvious that this distance is A, this distance is A, so let me not write anything about it, okay? So there is no scale actually, I want to take the help of the scale. So this distance of M from the center of the dipole is R, and this angle is theta, means the point M makes angle theta with the direction of the dipole. Dipole is in this direction, so it makes angle theta with the direction of the dipole. Let me take your dipole as P. Okay, is your dipole. Now what can I do? Okay, in your book, in your NCERT book, things are given in different ways. The joint BM, there will be two potentials at M, right? One is due to discharge, one is due to discharge. You find out the potential at this point due to both the charges and then add them up, right? and then add them up, that will give you the net potential at point M. But in order to do that, you need to determine distance BM, and then you need to determine the distance AM. So that's a kind of long procedure. So I want to skip that part. So I'm going to do it in very different way, or one of the easiest way, if you can recall these two relations, okay? Now what I'm going to do is, I'm going to resolve this dipole into two components. Example, how to resolve a vector. Suppose your F is acting along this direction. A force is acting in this direction. And the force makes an angle theta with this line OX. Okay? Then the component of F along this OX will be F cos theta. And with this F cos theta, you draw one perpendicular, right? So this component of F will be F sin theta. Is it okay? Yes. So the same way, this is your dipole, AB is your dipole, it's in this direction, right? Okay. So I'm going to resolve this dipole into two components. One is, this is your dipole. Suppose, assume that this scale is your dipole. You take the scale, okay, this scale is your dipole. If you keep the dipole along the angle theta, right? Now, if you keep the dipole along the angle theta, that will be your dipole is P. This is your dipole, it's P. So P can be resolved into two components. One is along the angle theta, that will be P cos theta. And one is perpendicular to this P cos theta, that will be P sin theta, right? Now, I'm resolving the dipole into two components. One is along OM. It is along the angle theta, that will be P cos theta. And one is perpendicular to your P cos theta, that will be P sin theta. So perpendicular to this OM will be this one, right? Is it okay? No? Ito OM logo perpendicular recta banalito ho na eh. Are you following that? No? So I'm resolving the dipole. I have denoted this dipole by P. And if you resolve this P into two components, along this OM, means along the theta, along the angle theta, along this OM, your dipole will be P cos theta. And perpendicular to this P cos theta, your other component will be P sin theta. That means there are two dipoles now. Your first dipole is P cos theta, and your second dipole will be P sin theta. Is it okay? So, the net potential at this point M will be not due to one dipole, but due to two dipoles. That is P cos theta and P sin theta. Now, for the first dipole, P cos theta, where is M? This is your first dipole, right? For the first dipole, P cos theta, where is M? On the axial line or on the equatorial line? On the axial line. See, for the first dipole, this is your first dipole, P cos theta, M is on the axial line. So this will be the potential at M due to P cos theta. Okay? And for the second dipole, P sin theta, where is your M? Where is your M? On the equatorial line, right? On the perpendicular of the dipole, right? So for the second dipole, P sin theta, your M is on the equatorial line because M is making an angle of 90 degrees with your dipole. Now, second dipole. So M is on the equatorial line. Okay, so the potential at this point M due to this dipole P sin theta will be 0. So the net potential at M will be potential due to the first dipole P cos theta, which is equal to this because it's on the axial line, plus the potential at this point M due to this dipole P sin theta, which is on the equatorial line, so 0. You sum up those two, then we get the required expression. Are you getting that? Now, very simple, no? This is the easiest way to do, okay? So let me highlight you again. Okay, let me just do it again. This is your dipole. Dipole means it's a system of two equal and opposite charges separated by some distance apart, let's say 2a apart. This is your point A, this is your point B, this is the center of the dipole. So I want to find out the electric potential at any point M at a distance r from the center of the dipole, making an angle theta with the direction of the dipole. Direction of the dipole is from negative to positive, right? So let me mark that point M. So this is your point M, which is at a distance r from the center of the dipole, and then it makes an angle of theta with the direction of the dipole. Now what I'm going to do, there is another procedure. In order to find out the net potential at this point M, okay, there will be a potential at this point due to this charge. There will be a potential at this point due to this charge. So you can find out those two potentials and then sum up, that gives the net potential at M. But finding the distances becomes a problem. Okay, so the easiest way is what I'm going to do. This is your dipole. Let's say P is your dipole. This dipole is P, okay? So I'm going to resolve P into two components. First, along the angle theta, that is OM, right? So if you resolve this dipole into two components, the component of this P along theta, that is along OM, will be what? P cos theta. And perpendicular to this P cos theta, you have another dipole, P sin theta. Is it okay? So the net potential at this point M will be now not due to one dipole, but due to two dipoles. Okay? Now, see, for the first dipole, P cos theta, you have two dipoles now, one is P cos theta, one is P sin theta. For the first dipole, P cos theta, where is M? M is on the axial line, on the same axis. Is it okay? And we know that the electric potential at any point on the axial line is given by this relation. The other one is, there will be a potential at this point M due to the dipole P sin theta. For this dipole P sin theta, M is on the equatorial line because it's perpendicular to this. Is it okay? Perpendicular bisector. So for this dipole, M is on the equatorial line. And we know that electric potential on the equatorial line of the dipole is 0. Is it okay? Yes. So the net potential at M due to the dipole will be only due to P cos theta, not due to P sin theta. Okay? Because the potential at M due to this P sin theta is 0. Why? Because for this dipole, M is on the equatorial line. So therefore, net potential at M will be due to what? The potential will be the potential due to this dipole P cos theta plus potential due to the dipole P sin theta, right? For the first dipole P cos theta, M is on the axial line. And for the second dipole P sin theta, M is on the equatorial line. Alright? Okay? Now we know that the electric potential on the axial line of the dipole is given by what? 1 by 4 pi epsilon naught into P upon x square minus a square. But this time, what is your dipole here? Not only P, it is P cos theta. So you have to write P cos theta, right? Plus the potential at the M, at point M, due to this dipole P sin theta will be 0. Why? Because M is on the equatorial line, and we already know that the potential at any point on the equatorial line of the dipole is 0. So your resultant, your net potential at M due to the dipole will be only 1 by 4 pi epsilon naught times P cos theta upon x square minus a square. Clear? Now, if the dipole is of very small length, special case, if the dipole is of very small length, that means A will be much, much less as compared to R. Here see, distance of this point M from the center of the dipole is R, right? That means X has to be replaced by R. X has to be replaced by R. Is it okay? Or you could have taken this distance to be X, no problem. Alright, you could have replaced this R by X, then same thing. So if the dipole is a very small length, then A will be very, very less as compared to R. In that case, A square can be neglected. As compared to R square. In that case, your net potential at the point M due to the dipole will be 1 by 4 pi epsilon naught P cos theta upon R square. That is the required relation for the electric potential at any point due to the dipole. So this is a very important relation for your examination point of view, okay? So you can just note it down. So the next topic, a very, very important topic. Relation between electric field and electric potential difference. There will be potential difference. The potential difference between any 2 points 1 and 2. Okay, the potential difference between 2 points 1 and 2. Suppose you have placed the charge Q naught at 1. So work has to be done by the external agent in bringing from this point to this point, right? Work is done by the external agent. Okay. So the potential difference between 2 points is given by final potential minus initial potential. Del V. Okay. So we need to discuss about relation between electric field and electric potential difference. Electric field is a vector quantity. Electric potential difference is not a vector quantity, alright? In order to study this one, you need to have some concept about partial differentiation, which you have not studied till now. You may study in maths class 12, I think, in differentiation. I don't know where, I forgot whether it's there or not, okay? Partial differentiation. So relation between electric field and electric potential difference. There are two cases here. Case 1. Case 1. If the field is uniform. Okay? Suppose if electric field, case 1, if electric field is uniform. What is uniform? Uniform school uniform. What is uniform? Constant. Okay? So we'll derive the relation between these two when the electric field is uniform. Suppose this is your uniform field. This is your uniform field. Okay? I have discussed this one once before. If you place a positive charge, inside this field, where will it go? In the direction of field. Okay? If you place a positive charge inside a uniform field, then it will go in the direction of the field. If you keep a negative charge in this uniform field, then it will go away from the field. And we have used that concept when we are finding the expression for torque on a dipole placed in uniform electric field, if you can remember that. Okay, I can remember that. So you have a uniform field, and I want to find out the electric potential difference between 2 points 1 and 2. Okay, alright, such that the displacement from 1 to 2 is given by delta R. Delta R is the displacement from 1 to 2. Okay, so displacement vector, right? It's a vector quantity. In order to do that, I need to keep a charge say Q, a positive charge say Q, or a test charge Q not say at 1. Is it okay? Huh? 1, matlab, just say Q is a negligible positive charge, test charge, okay? Then what will happen? Since Q is a positive charge, it will move in the direction of the field. That means it is experiencing some force, right? Right? Exerted by this field. What is that force equal to? That force is equal to what? No. Electric field is defined as force experienced per unit charge. So the force will be given by Q times E. Right? So this charge Q placed at 1 will experience a force in the direction of the field known as QE. Now, so this charge will experience this much force and it will move in the direction of the field. Is it okay? Now, if I let this force do the work, then there will be change in speed. There will be change in kinetic energy. But my aim is there should be no change in kinetic energy. There should be no change in kinetic energy. Okay. Potential difference between any 2 points, VA minus VB, is given by work done per unit charge, right? Work done by the external force per unit charge in taking it from B to A, right? Okay. So there should be no change in kinetic energy. Since yesterday I have been telling you this previous class, but since you did not ask me any questions, so I'm going to ask you from here. Actually, you should have asked a question from here, okay? Why there should be no change in kinetic energy? Kile. There could have been change in speed, right? There could have been change in kinetic energy of Q, but why I want that there should be no change in kinetic energy of Q? Work done, matlab, like? See, in case, if there was change in kinetic energy, then what will happen? Some of the work done will be converted into kinetic energy. That means the whole work cannot be converted to potential, into electric potential. Our aim is, I want to convert all of the work done into potential, electric potential. Now, all of the work done should be converted to electric potential. Only then this expression will be correct. Otherwise, if there is change in kinetic energy, some work done will be invested on this kinetic energy. So the whole of the work done cannot be converted to potential energy. And hence, electric potential energy. And hence, this expression would become wrong. Is it okay? Yes. So as to convert whole of the work into electric potential energy, we do not want any change in kinetic energy. No work should be lost. Okay? Yes. So see, if I let this force is acting in this direction, right? In the direction of the field. So if I let this force do the work, then there will be change in kinetic energy. If there is change in kinetic energy, the whole work cannot be converted into electrical potential energy. So what do I have to do? I have to apply an external force, right? And I have to apply an external force, which is equal and opposite to this force. So that without any change in kinetic energy, now I have to apply an external force, which is equal and opposite to that force QE. only then, without producing any change in kinetic energy of the charge, I can take it back. I can take it to the point 2. Alright? Are you clear about this? Yes. Now there is one point that you need to remember, a very important note. It's like this. Potential always decreases in the direction of the field. Potential always decreases in the direction of the field. That is a very important mark. Potential always decreases in the direction of the field. Yeah. So the potential, the electric potential at any point is given by what? 1 by 4 pi epsilon naught into Q upon R, right? Right? So this is your charge Q placed at this point A. If you're then the electric field will be in this direction. Then see, suppose this is your point A1, this is your point A2, this one is your point A3, and so on, such the distance between each of these points is equal to 1 meter. Now, distance between each of these points is 1 meter. Then, at this point there, the potential will be 1 by 4 pi epsilon naught into Q upon 1 meter. At this point 2, potential will be 1 by 4 pi epsilon into Q by 2 meters. Which one is greater? V1 or V2 is greater? V1 is greater, right? So the potential always decreases in the direction of the field. That means V1, okay. Now, so due to this external force, under the action of this external force, I can bring this charge Q naught from this point to this point too, without any change in kinetic energy. Is it alright? Now see, the external force that I'm applying is equal and opposite to this Q here, right? So the external force applied is equal but opposite to that of QE. I'm writing direction also, so you need to write in vector. Is it okay? And what is the displacement made here? What is the displacement made here? Delta R is the displacement from 1 to 2, right? Is it okay? Yes. Therefore, the potential between these 2 points, the potential difference between those 2 points, V2 minus V1, V2 minus V1, V2 minus potential difference between these 2 points means final potential minus initial potential. Is it okay? Yes. So the potential difference between those 2 points, okay, is given by work done by the external agent in bringing the charge Q from position 1 to position 2 per unit charge. This is what I'm going to use. So in order to get the potential difference between these 2 points, first of all, I need to find out what is the work done by the external agent, right? In bringing the charge from 1 to 2, right? Is it okay? Only if I calculate this work, I can find out the potential, correct? Yes. Now you see, work done here, work done by the external agent in bringing the charge from position 1 to position 2 is given by force into displacement. Here your external force, dot displacement. Yesterday I told that work done, this formula is applicable only if the work is done by a constant force, right? If it is a variable force, then we have a different relation for work done, right? Now why I'm using this relation here? Because here the force that I am applying opposite to this force is constant. Why constant? Because your field is constant. Since your field is constant, this Q will experience a constant force. Is it okay? So in order to make sure that there is no change in kinetic energy of Q, I have to apply a constant force opposite to that of force QE. Constant force, that external force is constant, right? Okay. So since this F external is constant, so we use this formula, force into displacement. Correct? Are you clear with this? Constant force, okay? So your F external, what is your F external? Minus QE. So minus QE dot dr. Now you see, your E is in this direction. Displacement is also in the same direction, right? So angle between E and dr will be 0. So minus Q vector E dot vector dr will be E dr cos 0 degree. E dr cos 0 degree, correct? In that case, this will become minus QE times dr. Alright? Therefore, the electric potential difference between 2 points 1 and 2 is given by final potential minus initial potential is equal to work done by the external agency in taking the charge from 1 to 2 upon the charge. Correct? Now, V2 minus V1 delta V. Delta V is equal to W external, work done by the external agency is minus QE dr upon Q. So your delta V is equal to minus E dr. Is it okay? Yes, it will be minus E dr. Now, why we are getting a negative sign here? Why are we getting a negative sign here? Do you have any question on that? Why are we getting a negative sign over here? Why negative sign here? Because I'm finding V2 minus V1, which is at a higher potential. 1 or 2? 1 or 2. Potential always decreases in the direction of the field. So which is at the higher potential? 1 is at the higher potential. And I'm writing V2 minus V1. That means lower potential minus higher potential will give you negative potential. Is it okay? So we are getting a negative. But if you consider only the magnitude, then we will write only E dr. Okay? Or if we consider only the magnitude, then we will write E dr. So this is the relation between electric field and electric potential if the field is uniform. This is not always true. This formula is not always true. This formula is only true when the field is uniform. But it's not like always, it's not that the field will always be uniform, right? Is it okay? Yes. Suppose you want to keep it in vector form. If you want to keep it in vector form, then this is how you have to find out the work done, right? Will be your work done. So in that case, your electric potential difference, V2 minus V1, will be given by minus Q E dot dr upon Q. Q cancels, right? V2 minus V1 means final potential minus initial potential del V, which is equal to minus E dot dr. We are getting negative. Why? Because V2 minus V1. V1 is at a higher potential than V2. So V2 minus V1 means lower potential minus higher potential, so negative potential. Actually, this is the required expression for the relation between electric field and electric potential difference if the field is uniform. But if you consider only the magnitude, then magnitude of your potential will be E dot dr in vector form. Is it okay? If you consider only the magnitude, then you have to remove this negative, then E dot dr. Alright? but we usually use this. If you consider only magnitude, we can use this. This formula is not always true because the field is not always uniform. Now, basing on this, I want to give you a small problem. We have not gone for the case 2, okay? Case 2 will be if the field is non-uniform, right? So there will be a small question, and I'm going to give you choice on which is correct. What is the unit of electric field? Unit of electric field. Force per charge. So unit will be per coulomb, right? So you have a uniform field. Your field is, let's say, 10 Newton per coulomb. Your electric field here is 10 Newtons per coulomb. You have two plates placed inside this field, plate A and plate B. Plate B has a potential. Plate A has a potential of 20 units, and you want to determine what is the potential at this plate B, right? And you need to focus on the direction of the field here, okay? Now, what is the potential at B? What is the electric potential at B? Roman 1, is it equal to 0 volt? Roman 2, 20 volts. Roman 3, 30 volts. Roman 4, 10 volts. Options are also provided to you. And what is the relation? Electric potential difference is given by minus E dot. You can use this relation. In magnitude, your del V will be only equal to E dot. Okay, in magnitude, right? If you consider only the magnitude, then you just remove the sign. Sign represents direction. So using this relation, can you just work out what will be the potential at B? Options are provided. All the informations are given. Okay, you have the formula with you. Okay, yes. Let's say that the distance between the two plates is 2 meters. Also, there is another distance between the two plates is 2 meters. So what will be the electric potential at point B? How will you do it? Here, okay, let me write the given information here. Potential at A, VA. VA will be equal to 20 volts, right? Your electric field is 10 newtons per coulomb. Distance between the plates, delta R, is equal to 2 meters. Alright? Yes. So what will be the potential at B? Now we know that del V is equal to E dot dr, right? Your del V. So del V is equal to, del V means difference in the potential, okay? Difference in the potential. So difference in the potential, del V is E dot dr. Your E is 10. Okay, before that, E dot dr means E dr cos of the angle between them. Angle between them is 0. Let's say that the displacement is from A to B. Alright? If the displacement is from A to B, then E and dr will be in the same direction, so angle is 0. So del V is equal to 10 times your dr or delta R, okay? Dr or delta R, 2 into cos of 0 is 1, so your del V is equal to, I used delta R before, right? Delta R, no? In the previous expression, I used delta R, so instead of dr, I can use delta R. So, I'm getting 20. I'm getting 20, right? Yes. So what is the problem here? So the difference in their potential is equal to 20.
We need to find VB.
Huh?
We need to find VB.
Yeah. So the potential difference del V means what? Del V means difference, which is at a higher potential. Which is at a higher potential? A or B? A, because the potential always decreases in the direction of the field, right? So V A minus VB. Correct? Okay. Hey, you see here, eh? The difference in their potential is 20. Already the potential of A is 20. Only if the potential of B is 0, now the difference in their potential will be 20. Is it okay? We got the potential difference as 20. So only when the potential of B is 0, the difference in their potential will be 20. So the correct answer is 0 volt. Is it okay? And obviously it's 0. Why? Because potential always decreases in the direction of the field. Their difference is 20 now, and it decreases in the direction of the field. So this B will have lower potential than A. And only then if this potential of B is 0, difference in their potential will be 20. Only if this is 0, difference in their potential will be 20. Alright? Yes. Okay. Oh, we almost messed up this question. I was thinking something else, but two of you were suggesting something else. Now, if the field is non-uniform, case 2, if it's working on, if the field is non-uniform, if the electric field is non-uniform, okay. Now if the electric field is E is non-uniform, then maybe E will be something like this, right? No? It's non-uniform. Is it okay? Yes, E is non-uniform. And I want to find out the potential difference between these 2 points, 1 and 2. Let the position of this one be represented by R1. Position of this 2 be R2. Is it okay? It's not required, but you just write the positions. 1 and 2 is R1 and R2. Position of this point R1. Position of this point R2. And I want to find out the potential difference, okay, between the 2 points 1 and 2. Here the field is non-uniform. So at every point the electric field will be different. So at every point, okay, the force, see, due to this field, if a charge Q is placed at R1, then it will experience a force QE, right? Is it okay? And at every point, as you go from 1 and 2, at every point this force QE will keep on changing. Is it okay? In that case, it becomes difficult to apply the external force also. Is it okay? So what I'm going to do is, in between 1 and 2, I'm going from 1 to 2, I'm going to take a very infinitesimally small displacement dr. dr is infinitesimally small displacement from 1 to 2. Then since this is an infinitesimally small displacement, electric field here will be constant. Not infinitesimally small distance, something which you cannot imagine, so small, okay, lesser than the distance between maybe the protons and neutrons in the nucleus. Okay, maybe something that's small, right? Okay, so if this dr is infinitesimally small displacement, then the electric field over this dr will be constant. Okay, let's say that dV is the small potential difference across this distance. Is it okay? Then dV will be given by what? dV will be given by, according to the previous relation, minus E dot dr. In the first case, if the field is uniform, then we derive that del V is equal to minus E dot del R, right? The del R, right? If the field is uniform. And see, for this displacement dr, field is uniform, right? In that case, let if dV is the small potential difference over this small displacement dr, then dV for uniform field, dV very small potential minus E dot constant field dot del R means replaced by dr now. Are you getting me? Yes. Now let's make this easy. Shall we divide all of the displacement from 1 to 2 into small drs, right? So that the force, the electric field over all these drs will be constant, right? And let dV and so on be the potential across all those small displacements dr. Then the total electric potential difference. The total electric potential difference. Okay? Del V. Total electric potential difference between the 2 points will be given by integrating this dV. Means adding up all those dVs in small displacements dr, well, the field is uniform. Okay? From R1 to R2. Correct? So this is equal to R1 to R2, dV means minus E dot dr, correct? So your del V will be given by minus integration from R1 to R2, E dot. This relation is always true. Always true. Okay? This relation is true only when the field is uniform. If it is non-uniform, this is not true. But this is always true for whatever kind of electric field it is. Okay? So these are the two required expressions or the relation between E and dV. Alright? In your book it's given like electric electric field is a gradient of electric potential, and the way they have derived is also different, but I think this is the easiest way to remember the relation. Okay, so if this question is asked deriving the relation between E and del V, electric field and electric potential difference, then you can just sort out those two cases and write them. Okay. So now no nagamis because it's giving. Okay. Electric field E. If this electric field is in space, then it will have three components: along x-axis, along y-axis, and along z-axis, right? Now, if electric field is in space, then it will have three components. Let's say that Ex is the component along the x-axis. X-axis is represented by the unit vector I cap. Let Ey be the component of E along the y-axis, so j cap. And Ez be the component of E along the z-axis with unit vector k cap. You know why I'm writing I cap, j cap, k cap? Representing the direction of the 3-axis. And let the position vector of r be, suppose there is a point P whose coordinate is x, y, z, then the position vector of P will be given by xi cap plus yj cap plus z k cap, right? Position vector of P. Tomorrow in maths we are going to study vectors, we'll discuss all those things. So let the position vector of R be xi cap plus yj cap plus zk cap. If I write dr, then dxi cap dyj cap plus dz k cap, right? Okay. Now we know that the electric potential is given by minus of E dot dr. Okay, right? You can use del R also, no problem. Electric potential difference between any 2 points is given by minus E dot dr. If you consider only the magnitude, you can just leave out negative sign, but I'm just taking into account, okay? Minus, what is your electric field E? Ex unit vector I, Eyj cap plus Ez k cap. Those people who don't know vectors, this cap also can be very confusing, but you are now familiar with it, okay? And vector dr means dxi cap plus dyj cap plus dz k cap. Here, in dot product, I dot I will be equal to 1, which is equal to j dot j, which is equal to k dot k, right? But I dot j will be 0, j dot k will be 0, j dot k, k dot j, everything will be 0, okay? And then I dot k also will be 0, okay? Simple vectors. So minus, since I dot I is 1, so we have Ex times dx. I dot j is 0, I dot k is 0. J dot I will be 0, j dot j is 1, so Ey times dy. J dot k will be 0. K dot I is 0, k dot j is 0, k dot k is 1, so plus Ez dz. So we have minus Ex dx minus Ey dy minus Ez dz. Is it okay? No. What I am going to do? What am I going to do is, you listen to me very carefully. Your del V is now minus Ex dx minus Ey dy. Let me write below. Your del V is minus Ex dx Ey dy minus Ez dz. Okay? Yeah. People who take this kind of video class, not here, in Delhi, Mumbai, Byju's and Vedanto, those people, like, they used to sing with the students along when they are in the class. That makes really interesting. But here, if I do something like this, people will consider me as fool. Okay. What I want to do is, I want to differentiate both sides with respect to x. But del V has y component, z component, right? And I'm going to differentiate with respect to x. Then That's called partial differentiation. V2 तीनटा component আছে. होइले एकटा variable दे differentiate करबोले सिने दुईटा छाडी दिगेन. Partial differentiation. Okay? I want to differentiate this del V with respect to x, delta V with respect to x. And this delta V has three components, along x, along y, along z. It has three components, but I want to differentiate only along x. And I want to differentiate with respect to x. That means I'm leaving two other components of V. In that case, that type of differentiation will be called as partial differentiation. Are you getting me? And when I do partial differentiation with respect to x, I have to consider the variable y and z to be constant. Is it okay? Similarly, if I differentiate with respect to y, that means I'm leaving two other components of del v. That's only partial differentiation. Partially differentiating this delta v, okay? Similarly for delta z again, or dz again, the same thing. If I differentiate this delta v with respect to z, that means I'm neglecting the x and y components. Huh? That means I'm only partially differentiating delta v. Are you following that? Yes. So partially differentiating, differentiating with respect to x. Then delta v, I will write it as del v upon del x, differentiating this delta v with respect to x, partially delta. This is capital letter delta, this is small letter delta. We call it as del. Okay? We use for denoting partial differentiation. Correct? So this will be minus ex. I'm differentiating with respect to x. So dx upon dx. Dx will cancel. So del v. Don't say delta. This is delta v. This is del v. Del v upon del x will be only minus ex. Is it all right? If I partially differentiate with respect to y, it means I have to consider x and z to be constant. So differentiating x with respect to y will be 0. I'm thinking that z is constant. So differentiation of z with respect to y will be 0. Because differentiation of any constant function is 0. Here actually they are not constant function. But since I'm differentiating with respect to x, I have to think that these two are constants. Okay? So differentiation of this will be 0, differentiation of this also will be 0. Is it okay? Yes. Generally, okay, it's alright. Let me not make it more trouble here. Similarly, if you partially differentiate with respect to y, then I have to consider x and z to be constants. In that case, your delta v will become del v upon del y, differentiating with respect to y partially. Then I have to think that x is constant, z is constant. So minus ey and then differentiating with respect to y. So minus ey dy upon dy. Dy will cancel out, so minus ey. Similarly, partially differentiating with respect to z, then we have del v upon del z will be equal to, I have to consider x and y as constants. So minus ez dz upon dz, because differentiating with respect to z. So dz will cancel out each other. Okay? So your so your delta v now becomes it's very dim now. That's okay. Your delta v now becomes minus, okay, what is minus ex? What is minus ex? Del v by del x. Del v by del x into x, right? Into plus. What is minus ey now? Minus ey. I'm going to take minus ey, so I'm writing plus. Minus ey will be del v by del y dy plus. Similarly, what is minus ez? Del v by del z. Is it okay? Are you following that? No? Alright, now. You can just write this, note this down. Okay, so there is a question here. Your potential is given to be 2x minus y plus z. And you want to find out the electric field at this point and also to find the magnitude of E, okay? Very simple. What I'm going to do? Partially differentiate V with respect to x, and this will become del V by del x, right? Del V by del x means your minus EX, correct? Right? Yes, but wait. Del V by del x means del by del x of your V, 2x minus y plus z. Differentiation of x with respect to x will not be 0, but the differentiation of y and z will be 0, right? So this will become del by del x of 2x minus del by del x of y plus del by del x of z. This is 0, this is 0. 2 is a coefficient, not a constant, right? So we can come out. So del x by del x, zik, so 2. And this is also known as your minus x, because we proved that del v by del x is minus cx, right? Can you check del v by del x is it equal to minus ex? Correct, no? Similarly, differentiating v with respect to y, then del v by del y will be del by del y of v, right? Your v is 2x minus y plus z. Differentiation of x with respect to y is 0. Differentiation of z with respect to y is 0. So I'm going to differentiate only this minus y with respect to y. Minus comes out. Del y upon del y cancels, minus 1. Again, differentiating with respect to z. Then, what? Del v by del z is equal to del upon del z, 2x minus y plus z. Differentiation of x with respect to z is 0, y with respect to z is 0. So I'm going to differentiate only del z with respect to del z, z 1. So this is your minus ey, this is your minus ez, right? So your electric field E, therefore your electric field E will be what? What was that? What was the resultant? Minus del V by del X. What was that? See, you're okay. Yes, your electric field E means EX I plus EY J plus EZ. Okay, actually at this point 101, no? But here this is only 2, I cannot substitute these points. This is only minus 1, I cannot substitute this point. This is 1, I cannot substitute this point, okay? So EX, okay, EX, what is your EX? What is your EX? 2. EX is 2, so 2I. What is your EY? Minus 1. So minus 1J, minus 1J. Plus what is your EZ? 1. So 1. Actually there is minus also, but I can ignore that. Okay, alright. Your minus ex is 2. So what will be your ex? Minus 2i. Your minus ey is minus 1. So what will be ey? 1. So 1j. Your minus ez is 1. So what will be ez? Minus 1. So I got it. There is no space where I can substitute this point. So finish. Now I want to find out the magnitude of E. Magnitude of E, very simple. Let me give you an example. If A is a vector given by xi plus yj plus zk, right? Then the magnitude of A will be given by square root of x square plus y square plus z square. Magnitude of any vector. Alright. So since I know E, so therefore magnitude of E will be square root of minus 2 square plus 1 square plus minus 1 square. 4 plus 1 square root of 6. Finish. Alright?
1, 0, 1.
Huh?
The point given.
No, there is no x, y, z in which I can substitute this value. No.
That's just for sure.
Yeah. Actually, if there was x, y, z, I could have substituted these values. Okay? Because after differentiating x, y, z vanishes. There is no point I can substitute this value here. Alright? So, are you clear with that? Shall I rub it out? I'll give you another one, another question. Question number 2. Number 2 is, let me see the question. V is given to be x square y plus y square z. Find electric field E at the point 1, 1, 1. 1, 1, 1, and also find magnitude of E. This will be your number 2. Your third question, I'll give you 3 questions. Your third question, your V is given to be x square y plus y square z plus z square x. Find electric field at the point 1, 0, 1, and also find magnitude of E. If you can do this 3, that's enough for today. So let me just work out with this number 2. Okay, I can just leave out 3 once. If I can do 2, you can do 3 easily. Your V is, this is your V. So your del V by del x will be del by del x of x square y plus y square z. So that is del by del x of x square y plus del by del x of y square z, correct? I'm differentiating with respect to x. So y is constant here. So y comes out. And I'm going to differentiate only x square, right? Now, here, there is no x, so constant. This y and z are constant, so 0. Differentiation of only constant is 0. Here, y comes out. So, differentiation of x squared is 2x. So, that is 2xy. Similarly, what will be del v by del y? Del v by del y will be del by del y of x square y plus del by del y of y square z. X squared is constant, it comes out, so del y by del y cancels 1. Here z comes out, so del by del y of y square, del by del y of y square. X square plus z into 2y. So that is x square plus 2yz. Did you get this? Okay. And del v by del z will be del by del z of x square y plus del by del z of y square z. This is purely constant 0. Here y square comes out, so del z by del z, del z, del z, so y square. So your electric field will be Ex plus Ey plus Ez. Ex plus Ey plus Ez, correct? Ex means del V by del X, which is 2xy. Ey means del V by del Z, which is x square plus 2yz. I mean with I, j, I missed out ijk, okay? I missed out ijk. So your Ex is 2xy with I cap, Your Ey is x square plus 2yz with j cap. Ez is y square with k cap, correct? I'm not putting negative sign, I don't like negative sign. So 2 into, at the point 1, 1, 1. So x is 1, y is 1, I cap. X square, so 1 square plus 2 into 1 with j cap. Plus y square, y is 1. So 1 square into k cap. So that is 2y plus 3j plus k. So your magnitude of E will be square root of 2 square plus 3 square plus 1 square. There's a 4 plus 9 plus 1 square root of 14. Alright? Okay. The same thing with number 3.
That means this one is not correct. Or
No, it's alright. It's correct. We have taken negative sign also, no?